do it. I'm coming! Let's do it!
No. That's too much for me.
Like that.
There is hope. Follow the lead.
Let's do it! Let's do it.
Remember, my son. And the music.
Do it! Do it! morning, 父上。
Morning. The sun is nearly risen. You are late. Yesterday, you were slow. Today, move faster.
Hi, 父上。
Getting past me is the first challenge.
Hello and welcome to this virtual session. We're glad you can join us today. Rain, you can click on the widgets that you'll need to get the most out of this virtual experience. Secondly, Microsoft specialists are on hand to answer your questions in real time. So feel free to type in your questions using the Q&A window and we'll answer them as soon as we can. Lastly, we've provided some additional resources for you to supplement your learning. You can access them by clicking on the links in this section. Without further ado, I'll hand over to our speakers.
Hello and welcome to the AI Fundamentals course. My name is Andrew Conniff and I'm a Microsoft...
What did I say? Faster. What did I say? Faster.
In session 4, it's all about document intelligence.
What did I say? Faster.
Intelligence and knowledge mining.
What did I say? Faster. What did I say? Faster. What did I say? Faster.
With them. And then we're going to discuss how we can access those tools in Azure and help us create our own AI models. And then how to rapidly add AI to our applications and solutions with the pre-built AI model. So let's get started.
Good. There's weight behind your strike.
A big question about AI. We start with what is AI?
Don't go easy on your father. Pretend I am your enemy.
And then what are some common AI workloads and understanding where AI fits in the organization? And how do we add AI workloads in responsible ways? So here we're going to talk about the tools we use to guide us and help us be responsible in working with AI.
I'm getting better.
Artificial intelligence is when machines, like computers, can do things like
Show me.
normally require a human.
You win this match.
Things
I
that
will
most
cook
humans
tonight.
do daily, often subconsciously. We make predictions, or we recognize patterns, and we use information that's available with our experience to guide us. We intuitively know when something isn't quite right or doesn't fit a pattern. Humans with vision use sight to experience the world visually, identifying options and written words around us. And we communicate by writing and speaking and engaging in dynamic conversations, responding appropriately. We can extract information from multiple sources to extend our knowledge. So here we're listing common workloads individually. It's important to understand that we will often combine workload types, and some will overlap with the capabilities, and that is expected. For example, imagine a conversational AI solution that uses a chatbot to process an auto insurance claim. The bot relies on some natural language processing capabilities to make sense of input, such as I want to submit a claim,
Training is enough.
which can be
You have other obligations.
typed or spoken.
I am the daughter of one of Iga's greatest warriors. Don't I have a reputation to uphold?
You are also a daughter of Iga. That means caring for the people within it.
That's what I'm asking to do. I want to protect them.
Finally,
The
the
ego
claims
away.
data, including forms,
Share the
photographs, and other
responsibility.
artifacts might be
Community
indexed to extract
and
insights and create a
benevolence.
searchable knowledge store to
You
help
will
manage
bestow that
future
upon
claims.
Matsu today.
Auntie Matsu again.
Any day she needs you, you
At
will help her.
Microsoft, AI software
of our
development
neighbors.
is guided by a set of 6
Yes, 父上. Auntie Matsu kept me for hours yesterday.
clearing the wasp nest from her tree.
A model should make predictions of whether
I
the
kept
loan
getting
should be
stung.
No complaints.
approved without incorporating
You know why
any
we help our
bias based on gender, ethnicity, or other factors that might result in an
neighbors? Alone,
unfair advantage or
but
disadvantage
together.
to specific groups of applicants. Azure Machine Learning includes the capability to interpret models and quantify the extent to which each feature of the data influences the model's prediction. This capability helps data scientists and developers identify and mitigate the bias in the model. Reliability and safety is another key concern. Our AI systems should perform reliably and safely. For example, consider an AI-based software system with an autonomous vehicle or a machine learning model that diagnoses patient symptoms and recommends prescriptions. And privacy and security is obviously a huge concern. AI systems should be secure and respect privacy. The machine learning models on which AI systems are based rely on large volumes of data which may contain personal details that must be kept private. Even after the models are trained and the system is in production, it uses regardless of physical ability, gender, sexual orientation, ethnicity, or other factors. And transparency, all of our AI systems should be understandable. Users should be made fully aware of the purpose of the system and how it works, what limitations may be expected. Finally, we have accountability. People should be accountable for AI systems. Designers, developers, and AI-based solutions should work within a framework of governance and organizational principles that ensure the solution meets ethical and legal standards that are clearly defined. In this next section, we will discuss how the AI models we use are created and what tools are available to create your own models. The fundamentals of machine learning is in 5 parts. What is machine learning? Types of machine learning, model training and validation, what is deep learning, and what is Azure machine learning. So machine learning can be described as some variation on the following 4 steps. The training data consists of past observations in most cases. The observations include the observed attributes or features of the thing being observed and the known value of the thing you want to train the model to predict, and that we call that the label. In mathematical terms, you'll often see the features referred to use the shorthand variable names x, and the label is referred to as y. Usually, an observation consists of multiple feature values, so x is actually a vector or an array of multiple values, such as x1, x2, x3, etc. An algorithm is applied to the data to try to determine a relationship between the features and the label, and generalize that relationship as a calculation that can be performed on x to calculate y. The specific algorithm used depends on the kind of predictive problems you're trying to solve, but the basic principles is to try to fit the data to the function in which the values of the features can be used to calculate the label. The result of the algorithm is a model that encapsulates the calculation derived from the algorithm as a function, and let's call it f. It's f for function. So mathematical notation, y equals the function of x. Now, the training phase is complete. The training model can be used for inferencing. The model is essentially a software program that encapsulates the function produced by the training process. You can input a set of feature values and receive as an output the prediction of the corresponding label. Because the output from the model is a prediction that was calculated by the function, it's not an observed value, and you'll often see the output from the function y hat as shown on the slide. Supervised machine learning is a general term for machine learning algorithms in which the training data includes both the feature values and the known label values. So supervised machine learning is used to train models by determining a relationship between the features and the labels in past observations, and then predict them for the future cases. So regression is a form of supervised machine learning in which the label predicted by the model is a numeric value. For example, the number of ice creams sold on a given day based on the temperature, rain, and wind speed. The selling price of a property based on its size in square feet, the number of bedrooms it contains, and socioeconomic metrics for its location. Or the fuel efficiency in miles per gallon of a car based on its engine size, weight, width, height, and length. Classification is a form of supervised machine learning in which the label represents a category or a class. There are two common classification scenarios. So binary classification, the label determines is the item there or is it not there, an instance of a specific class. So to put it another way, the models predict one of two mutually exclusive outcomes. For example, whether a patient is at risk for diabetes based on clinical metrics like weight, age, glucose level, et cetera. So they either are or they are not. Or whether a bank customer will default on a loan based on income, credit history, age, and other factors. Or if a mailing list customer will open a positively marketed item to their demographic based on their past purchases. In all of these examples, the model predicts a binary true or false, positive or negative, yes or no type of answer for a single possible class. Multi-class classification extends the binary classification to predict a label that represents one of multiple possible classes. So, for example, the species of a penguin, we have, a deli, gentoo, or a chin strap based on its physical measurements. The genre of a movie, comedy, horror, or romance, or science fiction based on the cast, the director, and the budget. In most scenarios, this involves a known set of multiple classes, and multi-class classification is used to predict mutually exclusive labels. So for example, a penguin can't both be a gentoo and a deli. However, there are also some algorithms that you can use to train multi-label classification models in which there may be more than one valid label for a single observation. So for example, a movie could potentially be categorized as both science fiction and a comedy. Unsupervised machine learning involves training models using data that consists only of the feature values. So there is no known labels. Unsupervised learning algorithms determine relationships between the features of the observations in the training data. Clustering is the most common form of unsupervised machine learning. A clustering algorithm identifies similarities between observations based on their features and groups them together in discrete clusters. So an example of that would be similar flowers based on their size, the number of leaves, the number of petals, or identifying a group of similar customers based on their demographic attributes and purchasing behavior. In some ways, clustering is similar to multi-class classification in that it categorizes observations into discrete groups. The difference is that when using the classification, you already know the classes in which the observation is belonging to. So the algorithm works by determining the relationships between the features and the known classification label. In clustering, there's no previously known cluster label. The algorithm groups the data on the observations purely on similarity features. In some cases, clustering is used to determine the set of classes that exist before training a classification model. So for example, you might use clustering to segment your customers into groups and then analyze those groups and identify the categories of different classes. So high value, low volume, frequent small purchaser, that type of thing. You could then use your categorizations to label the observations in your clustering results and use that labeling data to train classified models that predicts to which customer category a new customer might belong. Now let's relate this to X and Y from the previous slide. In the ice cream sales scenario, our goal is to train a model that can predict the number of ice cream sales based on the weather. So the weather measurements for the day, temperature, rainfall, wind speed, and so on, would be in the features X, and the ice cream sold on each day would be the label Y. In the medical scenario, the goal is to predict if a patient is at risk of diabetes based on their clinical measurements. The patient's measurements, weight, blood glucose, etc., are the X, and the likelihood of diabetes would be, example 1 or 0, or no risk would be the label Y. In the Antarctic research scenario, we want to predict the species of a penguin based on its physical attributes. The key measurements, the length of the flippers, width of the bill, and so on, are the features X, and the species, for example, Adele or Gentoo, would be the label Y. Training is the heart of machine learning. It's where we teach the model to find the patterns in the data. We use an algorithm to adjust the model until the data fits as well as possible. After training, we have the model that we can test. So we use some of the data that we set aside at the beginning, and we call that data validation data. That's to test how close our model's prediction labels are to the actual labels. In the case of unsupervised learning, where we don't know the actual labels, we measure how well the model's prediction are predicted on the labels. So we're separating clusters. There are many types of evaluation metrics. The important thing to remember is that the goal of machine learning is to find a model that gets as close as possible to predicting the actual label. The best model can still have a margin of error. Deep learning is an advanced form of machine learning. It tries to emulate the way the human brain learns. The key to deep learning is that the creation of an artificial neural network. And this simulates the electrochemical activity in a biological neurons by using mathematical functions. So the artificial neural networks are made up of multiple layers of neurons, especially defining a deep nested function. So this architecture is the reason the technique is referred to as deep learning, and the models produced by it are often referred to as deep neural networks, or DNNs. You can use deep neural networks for many kinds of machine learning problems, including regression and classification, as well as more specialized models for natural language processing and computer vision. To better understand how deep neural network models work, let's explore an example in which a neural network is used to define a classification model for penguin species. So the feature data X consists of some measurements of a penguin. Specifically, the measurements are the length of the penguin's bill, the depth of the penguin's bill, the length of the penguin's flippers, the penguin's weight. And the label we're trying to predict, Y, is the species of that penguin, and there are 3 possible species it could be: Delhi, Gentoo, or Chinstrap. The process for inferencing a predicted penguin class using this network is: the feature vector for a penguin observation is fed into the input layer of the neural network, which consists of a neuron for each X value. So remember, those are the input values. So in this following example, the X vector is used for the input. They're showing like 37.3, 16.8, etc. The function for the first layer of neurons each calculate a weighted sum by combining the X and the W, the weight. So each neuron in a layer is connected to all of the neurons in the next layer. The results of each layer are fed forward through the network until they reach the output layer. The output layer produces a vector of values, in this case using a softmax or similar function, to calculate the probability distribution for the 3 possible classes of penguin. In this output vector is 0.2, 0.7, and 0.1. The elements of the vector represent the probabilities for classes 0, 1, and 2, our 3 penguin types. The second value is the highest, so the model predicts that the species of the penguin 1 is Gen2 in this case. The model learns the appropriate weights by iteratively passing the training data through and evaluating the predicted probabilities for each class against the known class label. So the weights are adjusted in each iteration to reduce the amount of error or loss between predicted probabilities. For example, the 0.2, 0.7, 0.1, and the values that represent the actual class label, for example, 0.0, 1.0, and 0.0 for the class 1 Gen 2. Microsoft Azure Machine Learning is a cloud service for training and deploying managed machine learning models. It's designed to be used by data scientists, software engineers, DevOps professionals, and others to manage the end-to-end lifecycle of machine learning projects, including exploring data and preparing it for modeling, training and evaluating the machine learning models, registering and managing trained models, and deploying trained models for use by applications and services. Reviewing and applying responsible AI principles and practices. Once you've provisioned an Azure Machine Learning workspace, you can use it in Azure Machine Learning Studio, a browser-based portal for managing your machine learning resources and jobs. And in that Machine Learning Studio, you can, among other things, do the following. You can import and export data. You can create and use compute resources. You can run code in notebooks. You can use visual tools to create jobs and pipelines. You can also use automated machine learning to train models, view the details of those trained models, including the evaluation metrics, the responsible AI information, and training parameters. You can also deploy the trained models on request and use batch inferencing. You can import and manage models from a comprehensive model catalog as well. In this demo, you will see how machine learning features can be used to train a machine learning model and to make predictions. Here we are in Azure, and I'm creating an Azure Machine Learning resource. I'm going to put it in my resource group, which is going to act as a lifecycle container for all of the things that I need for my tool. I'm going to go ahead and set my configuration, and then I'm going to do a validation and create step here. All right, there's my machine learning resource. And what I want to do is launch the studio. This is where the machine learning work is going to take place. And so we're going to do an automated machine learning step here, and we're going to do a regression count. So we're going to go in and create a new job, and we're going to fill out some configuration before we get to see what's going on. So we're going to give our job a name, and then we're going to set up our experiment name and our description. So as you go through here, you can go through, you can see the different configurations that you can create here. We're going to choose regression to get different results, or to, depending on what your data requires, to set things up. All right, so we're going to create a data asset. We're going to give it a name and a short description. All right, this is going to be our bike rental data. And I'm going to then get this and choose the correct one that I want. And we're going to approve our data set. And there's the path that we do for the upload, and we're going to go ahead and upload from folder now. So we're going to find our bike data, upload all of it, and give that a minute to do that. All right, looks like it's done. There we have our data. We're going to go next. So we've imported the data. We've connected it to our job. All right, we're going to make a couple settings here. So we're going to go ahead and we're going to choose the random forest and the light GBM. There we go. So there's different models for our base that we can use, and we're going to go ahead and set some other configurations here. The important thing is that you can see how powerful the tool is and how much control we have over each of our data imports, and the variety of ways that we can choose different base models and then choose different fine tunings. All right, we have everything set up. The status is complete. We've done our data ingestion. We're going to go through it, and we can see our details of what's happening. If we go to our metrics, we can see our predicted tree and our histogram there. Okay, so now we want to deploy the model. So we've gone through, we've trained it, our data's in there, we've given on our parameters. It should give us now a nice regression number. So that regression was on that the prediction tree. It should follow along that line. We're going to go ahead and deploy our model to an endpoint, and now we're going to go to that endpoint and see what's there. So we have our endpoint, it's succeeded. We're going to test it now. And to do that, we're going to put in some categories that work with our data. And there we go. We have a nice regression that falls on our line. And it's just that easy to test it and make it available. That's been a quick tour of Azure Machine Learning. The Fundamentals of Azure AI Service section is in 3 parts. Azure Basics, a brief introduction to Microsoft Azure. AI services available on Microsoft Azure, and Azure AI services. Microsoft Azure is a hyperscale cloud service, and what that means is cloud users can deploy resources, and there is quite a reserve of capacity in the cloud for scaling and expanding. You will see in our Azure portal in our demonstrations. In the portal is where we can view and create, update, and delete all of our resources, and many of the ways of connecting to Azure exist. We're going to show you the portal, but you can use the command line. There's various deployment tools and all the ways that you can connect. And you're going to see our resources when we create them are going to be in what are called resource groups. Resource groups are lifecycle containers, and we do all of our work inside the resources themselves, either right there in the portal, or as you'll see with AI, often in a studio environment that's designed specifically for that resource. We have already seen Azure Machine Learning and how machine learning forms the foundation of AI's predictive capabilities. Next, we're going to look at Azure AI services in the areas of Azure AI Vision, including the features image analysis and face and optical character recognition. We're going to look at Azure AI Language, including the information extraction, text summarization and classification, question and answering, and conversational language understanding. Azure AI Speech, including text-to-speech and speech-to-text, Azure OpenAI, and Azure AI Search. It's worth spending a little more time examining Azure's AI services, as they illustrate a pattern that is common for many AI app scenarios in Azure. To use Azure AI services, you must provision a resource in your Azure subscription. This can be a standalone resource, which is like a service-specific resource. AI Vision is a good example of that. Or the general Azure AI Services multi-service account. That resource encapsulates multiple services, and using the standalone is going to give you the ability to save costs and work specifically with that, and has its own security and its own rules. And outside of that, when we're using the larger ones, you'll be able to combine them and get that savings. AI services in a single Azure resource can be centralized for the management. So regardless of the type of resource you use, the client applications will consume that service that it provides by connecting to a REST endpoint. So it's an HTTPS address to which they can submit requests using resource-specific keys for authentication or managed identities. Now let's take a look at Azure AI Services in Azure. All right, here we are in the Azure portal. And this is my dashboard view. This is the home view here. You can see I can have my favorites. I can create resources. I can view all of my resources. And we have a sidebar menu, and then we have the front menu. So there's two ways you can configure this. If I go into create a resource, I can search for what I want to do. Here's OpenAI. And I can then choose it from the list on the marketplace, and I can find the different resources I want to create. Next up, we have our notifications bell. This is anything that goes on, and while you're working in there, you'll get notifications. And then we also have our settings, and then reporting trouble and feedback are all across the top. I can even open up a command line and interface with my applications directly inside of the Azure portal. Everything is in a resource group, so you can sort by resource group, and you can see that those are lifecycle containers, and we have many resources inside of one, and you can delete them all together if you want to. And that has been a quick tour of the Azure portal, how we create resources and how we delete them. Here we are in Azure AI Studio, and we're going to explore the content safety features. And the content safety works against one of our other items. So we've connected to our Azure AI multi-services account. And so note before we start, some of this content might be offensive because that's what we're looking for. So this is our text analysis. And so we put in some easy breezy text, and we get, this is allowed because it was we know in advance that what this text already has in it. Let's try something that should fail. So this is a violent content. Again, we don't need to read it what it is. We know what the result should be. There it is, it's blocked. But what if we change our tolerance and we are more permissive? So this is going to give you a good idea of what's happening. So here I have a threshold. My threshold is higher. I'm going to be more allowing. We're going to do the violent content again. We're going to run the test, and this time it's allowed. So this is a great way to test your content filters against text you might experience to see what the result would be in your applications or in your AI solution. In this session, we learned how AI models are created with machine learning and neural networks. We discussed the many types of AI models we can include in our solutions and how to access AI in Azure. We're going to take a 10-minute break and come back with session 2, Fundamentals of Computer Vision. Welcome back from the break. This session is about computer vision and how the models are trained and how we're going to use them in our solutions. So let's get started. Our session on computer vision is divided into two parts. It's going to be computer vision concepts, and the second part is computer vision capabilities in Azure. Computer vision concepts cover three main points. So what is Azure AI Vision, the application of Azure AI Vision, and Azure AI services? We start with image processing. So digitized images are made up of pixels. A grayscale image that consists of an array of pixels that are valued between 0 and 255 are white. So color pictures, they're consisting of three arrays. This is our RBG or RGB channels that are going to be red, green, and blue. So that's the difference between the two. Most image processing involves the application of filters, which consists of kernels that define an array of weighted values. So the filter kernel is convolved or passed across and down over the image, and it's going to calculate the values for the new array using the weighted sum of the original pixel value. So because the filter is convolved across the image, this kind of image manipulation is often called or NNs used filters to extract the numerical feature maps from images. And then we feed those feature map values into the deep learning model to generate the label for prediction. So feed those in as X values. So for example, an image classification scenario, the label represents the main subject of the image. In other words, what is this an image of? You might train a CNN generated weight values. Then, as the process progresses, the model's predictions are evaluated against the known labeled values, and the filter weights are then adjusted to improve the accuracy. Eventually, the trained for images classification model uses the filter weights that best extract the features that help identify the different kinds of fruit. The following diagram illustrates how a CNN for an image classification model works. Models with known labels, for example, 0 for apple, 1 banana, 2 or orange, are fed into the network to train the model. One or more layers of filters is used to extract features from each of the images fed through the network. The filter kernel starts with randomly assigned weights and generates an array of numeric values called feature maps. The feature maps are flattened into a single dimensional array of feature values The Microsoft Florence model, which is used for image analysis 4.0 capabilities in the Azure AI Vision, is a multimodal model. So it's trained with huge volumes of captured images from the internet. It includes both language encoder and an image encoder. Florence is an example of a foundation model. In other words, a pre-trained general model on which we can build multiple adaptive models for specialized tasks. For example, you can use Florence as a foundation model for an adaptive model that performs image classification, identifying which category of an image belongs, or object detection, which is locating individual objects within an image, captioning, which is generating appropriate descriptions of an image, or tagging, which is compiling a list of relevant tags for that image. In this next section, we will discuss image analysis with Azure AI Vision Service, detecting faces with face service, and reading text with optical character recognition. This table illustrates the resources for computer vision and how they're divided in Microsoft Azure. The image classification and object detection, optical character recognition, and spatial analysis fall under the vision service. And for the specific models for detecting and recognizing faces, those are in the face service. The Azure AI Vision image analysis service can extract a wide variety of visual features from your images. For example, it can determine whether an image contains adult content. They can find specific brands or objects, or it can find specific objects or text within the image. While the AI Vision service provides some basic face detection and analysis features, the face service offers additional capabilities. All users can use the face service to detect blur, how blurred the face is, in which case it indicates how likely the face is to be the main focus of the image, or exposure, like aspects like underexposed or overexposed, and it's going to apply to the face in the image and not the overall image exposure. Whether the person is wearing glasses, the head pose, the face's orientation in a 3D space, and even noise, which refers to visual noise in the image. So if you have taken a photo with a high gain setting for darker situations, you might notice noise in the image, which is like grains or dots. Occlusions are objects blocking the face in the image. So it's important to note that anyone can use the face service for that. We can detect the location of the faces of an image. We can determine if the face is wearing glasses, determine if there's the occlusion, blur, noise, over, under exposure. And it can also return the head coordinates and the pose. The model makes no prediction about the faces it detects, allowing responsible use for a wide audience. However, to support Microsoft's responsible AI principles, facial recognition is under limited access policy. And the reason is it has the ability to compare faces for similarity and the ability to identify named individuals in an image. So we've discussed the computer vision service and its use in image analysis, but it also provides optical character recognition, or OCR, capabilities that can detect and extract text from images. So the service is provided in the Read Application Programming Interface, or API, and software developers can use that to extract both printed and handwritten text from images, from immediate reading of small amounts of text in images to asynchronous text extraction from large documents. We have 3 demonstrations to cover now, and they are the analysis of images in Vision Studio. And in this demo, you're going to see the AI Vision service and analyze images. Also detect faces in Vision Studio. We're going to look at the faces of detection capabilities of Azure AI Face Service. And then in Vision Studio, we're going to see that AI Vision's optical character recognition capabilities in action. So let's go to those now. Here we are in Azure AI Studio, and we're going to work with our images. So we're going to scroll down and we're going to find our Vision and Document section, and we're going to move to Image Analysis. So we're going to do Common Object Detection first. And I'm going to go ahead and connect to my hub, and then we're going to choose an image. So here we have, here we go, footwear, person. And you can see the bounding box showing up on there. Let's try another one. Bicycle, it has 3, and then when we change our threshold value, see it went for the bigger objects. Let's take a look at image captioning. And here we just want to caption for the image. This is going to give us a man holding a surfboard. That's great. Let's go back. Let's do dense captioning. So dense captioning is going to give us a lot more from the image. So here we're going to see a close-up of a ball of pasta, a close-up of noodles, blurry image of food, that type of thing. And it gives us the bounding boxes again. Let's try another one. This one is a man driving a tractor, the blue sky above a hill. So you can see how the dense captioning gives us much more information. Now we have image retrieval. So metadata about our images will help us find them in large pools of storage, right? So here I want sunset in the mountains from a list of 200 and some pictures, and I get 10 back, and I can be even more filtering, and I get like 6 back. Let's try that again. Here, let's go ahead and choose students using laptops, and let's trim that down to a much more usable number of images. There we go. All right, common tags. Look at all the tags we're getting. And we get a confidence level with them so we can sort those out in our applications. All right, text from images. Here you see we get the text and the bounding box for where it is on the item. And so the key value pairs are there. And those were included in the document. Here's another one with the credit card. We get the different parts of the credit card number, and then the valid dates and the name and all of that. Let's try the bicycle one. There we go. The life is like riding a bicycle. You see we get all of the text that's coming out of there. And this has been, let's do nutrition facts too before we go. Let's go look at this. This might be a good usage of that. We have, you see how it comes back, saturated fat or trans fats or calories, all of that works together. And then detect faces. So this is, we're not learning anything about the faces, we're just detecting them. And this is gonna tell us if they're wearing a mask or not. You see there's face 1, face 2. Again, there's face 1 because there's only one person, and this one has a mask, you can see. And that's been a quick tour of image analysis in Azure AI Studio. So we've looked at the computer vision in Azure, and we discussed the various ways we can gain insights from images. From knowing if an image is a banana or not, or if there is a banana in the image somewhere, or to pulling text from an image or removing a background. We finished with understanding facial recognition and the difference between detecting if a face is in an image and gaining insight about the face itself. This concludes our session. We're going to take another 10-minute break and come back with session 3, Fundamentals of Natural Language Processing. I'll see you back in a bit.